Hello everyone. Today's problem was submitted by a viewer and it says, find all compact subgroups of the non-zero complex numbers under multiplication. Okay, so before I get started on this, I should say I read the question, which was submitted by the viewer a couple of days ago. So I have had time to think about this in the back of my mind, although I haven't actually written anything down on paper. And I believe I know what the answer is after having thought about it for a while. But I'm also going to try and give my first thoughts when I first read this. So, my first thought is this sounds like a really complicated question because, think about what all the compact subsets of the complex numbers would look like, and you can have you might have some weird interaction with, you need a set which is closed under multiplication and compact. I don't know. I at first I thought this was going to be really, really difficult. But in fact, once you think about a couple of properties that this set must have, or if you think about how you might sort of construct contradiction from some assumptions or something like that, it actually becomes quite simple. So let me start with what my first sort of approach is going to be. So if we think of this as the complex plane, we have all the complex numbers except for 0. So the viewer who submitted this denoted this by C star, or you can think of this as like C minus the origin. So the origin is not actually in the entire set here. The other thing to understand is because we're working with essentially R2, we're working in two-dimensional real space, compact is equivalent to being closed and bounded. So we need sets that are closed and bounded and that are closed under multiplication and have all of the, closed under multiplication and have inverses and an identity, okay? So one of the first things I realized is that if there's any complex number which is not on the unit circle in a set, then automatically it cannot be compact. So imagine what I've drawn here is the unit circle. So this number right here, that's the complex number 1. Suppose we have some number with a modulus greater than 1. Let's call this z, where z has a modulus greater than 1. Well, if this number is in a subgroup, then z squared is also in the subgroup, z cubed is in the subgroup, and so on. All powers of z will be in the subgroup. But if I trace out z and z squared and z cubed and plot where those numbers are, z squared would be somewhere like here, z cubed would be somewhere like here. Basically, the modulus of z to the n goes to infinity as n goes to infinity. And so if this number is in the subgroup, then that subgroup cannot be bounded, and therefore it's not compact. Okay, so this shows that any complex number greater than 1 with modulus greater than 1 cannot be in the subgroup. And we can do the same thing with a complex number whose modulus is less than 1. So if I just change this inequality like that, well, by similar arguments, now we have that the modulus of z to the n approaches 0 as z goes to infinity. And that means, we would then have a sequence of points which approaches 0 like this. And that collection of points cannot possibly result in a set which is closed. Because if it were closed, then the origin itself would also have to be in that set. So what I've shown so far is that a compact subgroup of this set, all elements must lie on the unit circle. Now, the unit circle itself is a subgroup of C star, and it's clearly compact, it's closed, and it's bounded. It is a subgroup because if I take any, let me get rid of these points here. If I take any 2 points on the unit circle and multiply them together, I will get a third point somewhere on the unit circle. There's clearly an identity to this operation. The number 1 itself is the multiplicative identity of complex numbers, and there are clearly inverses. If I just take the complex conjugate, multiply those two numbers together, I will always get back 1. That comes from, if you think of complex multiplication as rotations, then the inverse of this number is just going to be the one down here. Multiply those two things together, and we rotate back to 1. Okay, so it is a subgroup because the multiplication of any two numbers will stay on the unit circle. It has inverses and it has the identity. Okay, so we know every subgroup has to be a subset. Well, sorry, I've shown now that the unit circle itself is a subgroup, and any other subgroup which is compact has to lie on the unit circle. So the other classification of subgroups I want to talk about, if we think about complex numbers written in the form e to the I theta, where theta is the angle here. Any complex number can be parameterized by an angle like this and a modulus, but the modulus is always going to be 1. So e to the I theta is the way we denote this number, where this angle is theta. If I take a number z, which is e to the I times 2 pi over k, and k is equal to any positive integer. I'll write, I'll just write 1, 2, 3, any positive integer. So let's, how should I denote this whole thing? Okay, I'm gonna say fix k in the positive integers. So k is 1, 2, 3, 4, and so on. And let z be equal to e to the I times 2 pi over k. Then let g be equal to z, z squared, z cubed, z to the 4, and so on. So eventually this collection starts to repeat itself. In fact, it goes all the way up to z to the power of k, which is in fact equal to 1. Z to the k is equal to 1 because if I raise this to the power of k, I get e to the 2 pi I, which is the number 1. We've rotated around k. We've rotated by 2 pi over k times, so we get back to 1. So this will be a subgroup. It's finite. It's a finite collection of points in the complex plane, so it's clearly closed and bounded. It's in fact a cyclic subgroup because it's generated by a single element. Every element in here can be written as a power of z. And I claim, let's call this g subscript k, because it kind of, once you choose this integer k, this group becomes fixed by this definition. And I believe all subgroups, all compact subgroups, are either, I'll say, the set of any complex number with modulus 1, or gk for some positive integer k. So this is the unit circle in the complex plane. I've shown that that is a compact subgroup. GK is a compact subgroup, and I claim that there are no other compact subgroups. The reason why is because, first of all, it has to be finite. If I have an infinite number of points on the complex plane, or on the unit circle, if I have an infinite number of points in the unit circle, then I can create sequences which converge to something, and that point must also be in the set. So for example, if I have a sequence of points on the complex circle which converge to something, then the limit must also be in the subgroup, because otherwise it's not compact. And it has to be rotationally symmetric. Is that true? Does it have to be symmetric under rotations? Probably. Hold on, I'm doubting myself a little bit here. Like, I claim that the only compact subgroup with an infinite number of points is the circle. What exactly is the argument for why? Yeah, okay, so it has to, if any point can be multiplied by something to bring it to another point. And so this convergent sequence, I can make that convergent sequence, and let's say I have the correct multiplication to take this point and map it there. Well, I can apply that to every point so that this picture just rotates. And so in fact, this sort of dense limit thing also has to be at another area. Hold on a second. Oh my. I don't feel like I'm giving a proper argument for why. I'm not giving a convincing argument for why there can't be any other infinite subgroups. Okay, here's one way that I think this might make sense. Okay, suppose I have a complex number that is in my subgroup written like this. So x is the angle corresponding to the complex number. If x is irrational, okay, hold on. Suppose z is in a subgroup So suppose Z is in a subgroup and Z is Z has an irrational angle. Okay, so if the angle is irrational, then G has to equal the circle. Okay, if there is a single point in the subgroup where the angle is irrational, then the entire subgroup must be the circle. So here's why that has to be true. Basically, it's because if I take this number with an irrational angle, as I say it's this one, as I take all positive integer powers of this, I will keep going around the circle and I'll never repeat. And so that will create a dense subset of the circle. And if a dense subset of the circle is in the subgroup, then because it's compact, the entire subset of the entire circle has to be the subgroup, or the subgroup must be the entire circle. Okay, so this number alone, okay, basically what I'm saying is this number alone generates a dense subset of the unit circle. And because we're looking for things which are compact, that means every number in the unit circle must be in this subgroup. Okay, so if the subgroup is not the full circle, then any number in the subgroup, so now let's suppose G is not equal to, I'll just call it S1, the circle. Suppose G is not equal to the circle, then any Z in G has Z is equal to e to the 2 pi I x with x rational. Okay. And if I have two complex numbers, Z1, Z2, that are in the group, so Z1 is equal to e to the 2 pi I x1, and Z2 is equal to e to the 2 pi I x2. So this generates one cyclic group. In fact, let me write these as rationals. Let's call this pk over qk, p1 over q1, and this would be p2 over q2. With, of course, p1 q1 relatively prime, p2 q2 relatively prime. Then this will generate a subgroup which is in fact the same as the one I defined above. So Z1 generates G subscript Q1, and Z2 generates G subscript Q2. And the two of them together, Z1 and Z2, generate G of, I believe, the least common multiple of Q1 and Q2. So, if you just think about, for example, if I take let's just get rid of all these colors there. if I take G3 and G5, so G3 is these three numbers, and G5 are these five numbers, 1, 2, 3, 4, 5. Okay. If I'm also allowed to multiply any colors like that, then in fact what I get is G15. So, you know, if any rational multiples, and if the subgroup contains any two numbers with a rational argument, then it's really just the same as like coming from another subgroup. But you can kind of only make this argument a finite number of times. You can't just keep throwing in more rational arguments, because again, if you have an infinite number, then you're throwing in all of the rational angles, but that again is not a closed subset of the circle. The rationals are dense, and you kind of end up with the whole circle in some sense. Like, this doesn't, now that I'm saying this out loud, it's not like the most convincing argument, but I mean, I believe that this is the correct answer. All the compact subgroups are either the entire circle or one of these cyclic collection of numbers. I just can't see how you could have another infinite subgroup without having some kind of weird contradiction where you have, you don't have, the limit points aren't in the subgroup or something like that. Yeah, this is not a convincing argument, but I'm confident in everything I said up to, this is certainly a subgroup, and any subgroup has to lie on the circle. But I would need to, think a little bit longer about how to make this fully rigorous or convincing. Yeah, when I was thinking about this before writing down, the whole thought process was a lot more clear in my head. Anyway, I don't want to spend too much more time on this, especially considering I'm kind of rambling and would need to focus a little more on exactly how to convince myself that any non-infinite subgroup has to be basically one of these cyclic things. But like intuitively, I just think that's kind of true. It was a cool question. It ultimately didn't turn out to be quite as difficult as I thought, even though I feel like my answer is incomplete. I don't know if the user who submitted this knows exactly what the correct answer is. But if you let me know if this is the correct answer, and maybe what the fully rigorous argument is for why all of the non-infinite groups have to be this, that'd be really cool. I think I'm more or less on the right track. But yeah, I'll call this an end there. Again, I don't really have much more to say about this one, I don't think. So thanks for watching.